TAO, or Test Time Adaptive Optimization, is a new methodology for fine-tuning LLMs that have been developed by the Databricks team, and essentially the main advantage of it is that it allows you, by just using an LLM, to tune it during a tuning phase to perform much better than its original state on a wide variety of tasks. I figured it might be a good topic to talk about, so I decided to make a video on it real quick and for us to go through the fundamentals of TAO and how it would work. This is the overview of the TAO pipeline. Essentially, what it means is that you have an LLM, let's say it could be something like Llama 70B or any other LLMs that you have, and the goal here is that when you have the pre-trained LLM model, you could have a fine-tuning phase afterwards, and then you can have, like, let's say, a usage phase after that. And during that fine-tuning phase, you're going to use test time compute in order to tune your LLM to do better on these tasks that you're using it for. What it will do is that you take your trained LLM, you let the users interact with it, which provides the usage data. And what happens is that using that usage data, it generates or uses inputs to your LLM. With those inputs, and again, it doesn't need outputs, you won't need advanced or expert annotations on these inputs, so you just need the inputs themselves. You will go and do response generation. So you're going to create responses for these, and then you're going to use the scoring. Now this scoring here is similar to, let's say, what you've been seeing in reinforcement learning approaches like DeepSeek R1 and R0. What happens here is that this could be anything. It could be any sort of custom rules that you're using for scoring. It could be an LLM as a judge system. What they have is a proprietary reward system called DBRM, or Databricks Reward Model, which they mentioned that it works perfectly, or it works really good. But it could essentially be anything, and the only goal here is to compare these responses and make sure to provide signals for the LLM to make sure that as you're adjusting it, as you're tuning it, the responses that it generates are more aligned with the responses that have gotten top scores or highest scores in the response generation phase for these inputs. Now, what happens here, and is most important, is that even though this training happens using the test time compute, at the end of the day, once that tuning phase has been over, and once you have an LLM that works perfect on a system, you do not need to have access to any additional compute than what you needed to run the originally pre-trained LLM for the system. So it's not something that, for example, requires a long chain of thought prompts or things like that. It does not require a very extensive number of tokens in the output in order to make sure the alignments are better. So what happens here is that you just have like this tuning phase. You're using these data in that tuning phase, and you improve your model. Again, some of the key points is that it does not require labeled data because it just uses the test time compute. It just uses the inputs that are provided to the system, the inputs that are aligned with, let's say, the tasks that you're using it for, and it generates responses on its own. So you won't need to have a large number of labeled data in order to be able to tune it. And the great basically experimental or empirical result here is that it could use basically low-cost open source models like Llama series, and with those it could perform competitively with basically expensive proprietary models that work very great on these tasks. So what it uses is test time compute, and it uses reinforcement learning to perform this tuning. What matters here is that it scales with the adjustable tuning compute budget. So you would basically provide a compute budget and then basically limit it by that compute budget. As long as people continue using it and you still have not exceeded the compute budget, the LLM you have keeps getting better and better. So as you use it, it gets better. The three main results that they have talked about in this article are great performance in document question answering and SQL generation, multitask version of the test time adaptive optimization to perform better on many other tasks, and showing that TAO essentially scales with the compute budget for the tuning phase, and therefore you can essentially increase that tuning budget, and the more you use the model, it gets better. On these benchmarks, you can see that this one is essentially the bright red one is the TAO model. You can see that compared to fine-tuning Llama, it achieves much better result, and at the same time it's very competitive to the essentially big guys or big models like GPT-4o. You can see the same kind of result with Llama 3.18b, and you can see that increasing this tuning compute budget which in this case is a normalized value here, it would lead to kind of a scaling as you allow more budget for this tuning phase. And at the end of the day, if you want to use the test-time adaptive optimization in practice, the only requirements are that, first of all, a way to have access to sufficient number of example inputs. Again, outputs are not necessary super necessary here. So in the scale of over several thousands would be good. And then sufficiently accurate scoring methodology, which again could be anything like LLM as judge or process reward models or whatever. They are using DPRMs here, and essentially that is getting a lot of good results for them. Anyways, this was a quick summary of the test time optimization model, and I hope you found it useful. Thank you.